I'm Ian. This is Sam. Sam is going to be the DJ. I'm just the hype man. Um, uh, so let me just for calibration ask how many people here have read some code in a declarative programming language, Prolog, answer set programming, constraint programming? Okay. All right. And how many of you taken a class where they tried to teach you what unification was? Okay, good. All right, so I need the remote. All right, so Sam and I are interested. Sam and I are interested in large scale, sort of city scale character simulations where we've got large numbers of characters being simulated at relatively low fidelity for things like Dwarf Fortress, Talk of the Town, Bad News, things like that. And we want to make it easier to build simulations like this and sort of fiddle around with them and try and change them. So this is our TED Talk. We're going to talk about TED, which is Typed Embedded Data Log. And it's a logic programming language. So you are describing things in terms of relationships and rules for when those relationships happen. And it is in a lot of ways like a traditional logic programming language, but it's taking some lessons from data log from the database community. And so it's going to store the complete extension of every predicate in a table in RAM and then index the hell out of that. So we're doing bottom-up execution. It's nice because it has clean semantics for update, which you tend not to have in logic programming. And it's embedded in C# and it's very fast, as we're going to talk about. So, oh, and it has really good dev tools. You can do declarative breakpoints and assertions. You can say stop anytime this arbitrary query against the game state is true. And it will. And it's cheap. And you can turn it off and on easily. Because everything's being stored essentially in database tables and there are built-in visualizations, table visualizations, graph visualizations, and so on, just out of the box, you have live interactive visualizations for all of your data. And because it's embedded in C#, you have full IDE support. IntelliSense works. You can do refactoring. You've got all of that stuff. So look at the paper for more related work, but sort of the most focal things are in terms of systems for trying to develop these kinds of large-scale simulations. There's Neighborly by Johnson Bay and Kismet by Adam and Ben. And why did we advance? Okay, and there's been a fair amount of use of logic programming at this point in games, but in terms of things that are sort of in shipping games, the big ones are Inform 7, Versu, and City of Gangsters. Now I do want you to go forward. Okay, I'm just going to shift over here, I guess. All right, so what we wanted to do was a head-to-head comparison where we implemented the same thing in our language and in C# and compared to the code size and performance. So our benchmark is going to be a subsystem of a town-like sort of game. So you've got characters, you've got locations. The characters have affinities for one another. They have opinions about one another and about locations. And the basic loop is you go someplace you like, and when you're there, you talk to someone you're interested in, and depending on how the interaction goes, it increases or decreases your affinity for them. So you can describe that very abstractly and very compactly in a kind of declarative form like that. But if you write it in C#, if you write it in C#, it's 85 lines of C# code. But the good news is that even with 2,000 characters and 100 locations, it's 6 milliseconds per tick to update. So it's nice and fast. The problem with that is it easily took Sam and I an hour to write, and it embeds all kinds of assumptions about what's the data, how are you going to access it, What do you want to do a lot? What don't you want to do a lot? And so if you want to change things about the nature of the affinities, your representation of space, things like that, you're likely to have to do quite a heavy rewrite. And that means your designers can't experiment because making a change that might not be worthwhile is too expensive to do. So our goal is to make those changes cheaper to do so you can do more experimentation. And we're trying to do that by letting you write in a declarative form and then have the system generate the C# code that you would have written yourself. So why can't we do this in an off-the-shelf declarative language? Well, most of them are query languages. They're not designed to let you say, and now change this. And so a lot of them just literally don't let you say that at all. Some of them, like Prolog, let you do it, but the assumption is you aren't going to do it very much. And so it's like wildly inefficient. And they're not designed for real-time performance. So this is a partial implementation of our benchmark in Prolog. It's disappointingly large, but what matters here is that for the previous implementation, this number was 6. All right, so that's 4 orders of magnitude slower. Why is that? Well, Prolog has to do a lot of pointer chasing, garbage collection, runtime type checking, things like that. And mutable state just is not designed for this use case. This isn't because Prolog is bad. This isn't because SWE is a bad compiler. It's a magnificent compiler. It's not designed for this. And it's clunky because we have to do a lot of memoization manually, which then means more state management. And for those of you who know about table Prolog, we tried that. It breaks SWE's table Prolog implementation. All right. Now, really, in that example, it's the mutable state that's causing problems, but also I want you to think about what is Prolog doing when it's asking what's the value of integer variable x. It's doing the equivalent of the compiled and inline version of all that code, which means depending on how many forwarding pointers you have to follow, your best case is 2 nanoseconds to read, 5.5 nanoseconds to write. That sounds really fast, except that for C#, it's half a nanosecond. And that half nanosecond may well be pipelinable, and so it may not actually be increasing your execution time. So next, people ask us, why not use answer set programming? Well, you literally can't express this in answer set programming because answer set programming doesn't do floating point. It also doesn't do mutable state. And so here's our essentially one-line answer set programming implementation of this, just to assure people that we tried. It says there are 100 people, there are 100 time ticks. There is an affinity between every 2 people at every point in time, and it is one of 11 possible values. And that takes 10 gigabytes of RAM to execute, and it's not doing simulation. And I do not have enough disk space on my laptop to run this line for 2,000 people. All right. So here's the TED implementation. It's much more compact. It's not as fast as C#. I'm working on it, but it's pretty close. 7.5 milliseconds versus 6 milliseconds. And the real work is being done by those 4 statements. This is how you figure out where people move to. This is how you figure out who they interact with. These are how you decide how to update the affinities of characters. And you just crank that each tick. All right. So why is that fast? It's strongly typed. It compiles to C#. This doesn't benefit a ton from parallel evaluation because there aren't actually enough tables in it, but it does run multi-core. We have a very tight, efficient, cache-efficient representation of data. The bottom-up execution gives us lots and lots of caching of the results of our queries. And apologies for those of you who don't know about this stuff. The thing that's really important is that when you are unifying, you are always unifying against a ground term, which means you can never unify two variables against one another, which means you don't need forwarding pointers, which means that reading a variable is the same as in C#. We're really just compiling the code that looks like the code you would have written in C# in many cases. So implementation matters. And with that, I'm going to throw to Sam, who is going to do a demo of a town-like system built using this.
So, those of you that were here yesterday may have seen this in the demo session, but this is Voix de la Vie. It is my attempt at a talk of the town clone of sorts, and it is built using TED. Very similar to the demo problem that we used to compare TED to C# and Prolog. We, in this, so comparing this to TED, C# and Prolog, the little demo that we had, this is doing a lot more. So it's not just going to a location and doing work and interacting with a person, updating your affinity. In this, you also become employed, new locations spawn into existence when that is desired by the people in the town. People in the town form relationships that can turn into families, etc. and so on. This is a bit bigger of a program, but as you can see, it is still running pretty darn quick. The other thing to point out here is that
lines.
Oh yeah, 450 lines. So the other thing to point out here is the debugging tools that we mentioned during the paper. So table viewers here on the side, it's pretty easy to just inspect the whole state of the system. Yesterday, I think we had looked at gossip, but that's not in this one because slightly different version. So we can see who's romantic with one another in this table. We can visualize who works where, and all of these graph visualization and table visualization tools are pretty darn easy to use. The tables are automatically put together from your simulator. It finds all of the predicates and is able to display them. The graph stuff, you write a little function that decides what the edges will be between nodes. But with that, you are able to do graphical display of pretty much the entire state of your sim, as long as the entire state of your sim is in TED.